Let's take a look at an ideal gas problem. So we want to calculate the volume occupied by 0.85 moles of nitrogen gas at a pressure of 1.3 atmospheres and a temperature of 315 K. Now here's the question. Is anything changing? And the answer is no. Okay, we don't have a volume going to another volume, or a pressure going to another pressure, or a temperature going to another pressure, or a moles going to another moles. We just have individual values for moles. So if that's the case, you're looking at PV equals nRT to solve your problem. Okay, we're not looking at any of the other gas laws because they all involve changes in something, two or more things. Okay, so in this case, it's useful again to make a list. So we are interested in finding the volume. So PV equals nRT. Let's rearrange to solve for volume. nRT over P. Right? So once I've rearranged things, I'm checking first that all of my units are in the correct thing. So I have moles, atmospheres, kelvins. Great. And I already know the value for R. That's a constant, so I always have that in my back pocket. So we have volume equals 0.845 moles times the gas constant, liters atmospheres over moles Kelvin, times our temperature in kelvins, 315 K, and all over the pressure, 1.37 atmospheres. Now let's take a look at units for a second so that we can see how this is all working, so we understand how we end up at the correct unit. So in the top part of our equation, in the numerator section of the equation, moles divided by moles will cancel out. Kelvins on bottom times kelvins will cancel out. Atmospheres on top divided by atmospheres, that'll cancel out. So leaving me with the only unit left is liters, which is a unit of volume. So we should have 15.9 liters as our answer. All right, let's calculate the molar mass of a gas from the ideal gas law. Okay. Now there's a couple of ways to go about this, but we're going to do it probably the most simple way, given that we know the mass. So all we need in order to get molar mass, so molar mass, capital MM, is mass over moles, right? We already have this part, so what I need is moles. And I have volume, temperature, pressure, and R, so all I need to do is find N, okay? So I don't have anything changing in this equation, so that's usually a good way to start. Is there anything changing? The answer is no. So we're going to be looking at PV equals nRT, right? And we're going to rearrange to solve for N. PV over RT. Okay, so I can say 1.06 atmospheres times the volume times R, 0.8206 liters atmospheres moles Kelvin times the temperature, 298 K, and we get an answer of 4.8548 times 10 to the minus 3 moles. And let's not forget sig figs, so I'm going to track at the third sig fig. Okay. So our molar mass is mass over moles. So we were given mass in the problem here. So all I have to do is divide mass by moles to get the molar mass. So 0.136 grams divided by 4.8548 times 10 to the minus 3 moles. Tracking at the third sig fig, so my answer should be 3 sig figs. So we end up with 28.0 grams per mole. Right? So this very likely could be nitrogen gas, because Nitrogen N2 has a molar mass of 28 grams per mole. All right, moving on. So, partial pressures. So, partial pressures are related to mixtures of gases. Okay, so each individual gas has its own pressure within the container, and the partial pressure of a component equals the fractional component times the total pressure. Okay, and I'm going to get into that here in just a little bit. So sort of towards the end of this lecture, I'm going to come back to this. Okay, but the idea here is that looking at this mixture, and let's say that this is a mixture of helium and neon. So if my partial pressure of helium is 0.8 and my partial pressure of neon is 0.2, I add those together to get the total pressure of 1 atmosphere. Okay, but like I said, I'm going to get into partial pressures in more depth, how to calculate those from mole fractions in a little bit. In the meantime, I'd like to take a look at our next gas law, which is Dalton's law of partial pressures. Okay, and the idea with Dalton's law is that simply that the pressure total is just a sum of the partial pressures. So these are the partial pressures. So the partial pressure of gas A, partial pressure of gas B, partial pressure of gas C, and on for however many gases you have. Right? So thinking about what our air is like, our air is primarily nitrogen, oxygen, and argon, with lots of other gases mixed in smaller components. But if the partial pressure of nitrogen is 0.78, and the oxygen is 0.21, and the argon is 0.01, all that adds up to be 1 atmosphere, which is the pressure of our atmosphere, of our air. Let's take a look at an example problem here. Okay, so if we have a mixture of helium, neon, and argon, and that mixture has a total pressure, so pressure total pressure is 558 millimeters of mercury. The pressure of helium is 341, and the pressure of neon is 112. What is the partial pressure of the argon? Okay, so let's apply Dalton's law so that pressure total equals the pressure of the helium plus the pressure of the neon plus the pressure of the argon. So if I know this, and this, I can easily solve for the pressure of argon. So the pressure of argon simply equals the pressure total minus the pressure of the helium minus the pressure of the neon. So we have pressure of the argon. Total pressure was 558 millimeters of mercury minus the 341 for the helium minus the 112 for the argon, or for the neon. So that gives us the partial pressure of the argon is 105 millimeters of mercury. Right? Now, gases in chemical reactions. So we're getting into stoichiometry. Right? We've done lots of things with stoichiometry over the course of the semester. And all we're doing is building another route to the mole bridge. Okay, so everything in stoichiometry is related to moles. So now that we have the ability to deal with gases and calculate moles of gas, we can then use that to cross the mole bridge. But the idea is that the stoichiometry itself is no different. Okay, we may have to use ideal gas to get to moles, and may have to use ideal gas to get out of moles, or we may have to use solutions, molarity, to get to moles, and then ideal gas to get out, or vice versa. But this is just another path to calculate moles. Okay, but the idea is that, again, the stoichiometry doesn't change. All right, so given what we have here, and I'm going to cross this out and write it correctly balanced, so we should have 3H2 gas plus N2 gas gives us 2 NH3 gas. That was a bit of a typo when I first made this slide, and I apologize that it's still there. But so how many moles of ammonia are formed by the complete reaction of 2.5 liters of hydrogen at 381 K and 1.32 atmospheres? Assume that there's more than enough N2. So N2 is our excess, so we don't have to worry about it. But we are given volume, temperature, and pressure, and we always know R, because that's a constant. So I have everything I need to use the ideal gas law to find moles. Okay, so ultimately I'm going to use that to find moles of hydrogen, and then mole bridge to find moles of ammonia. Okay, but all I'm doing is I have a new path to get to the moles. So PV equals nRT, N equals PV over RT. So I have volume, temperature, pressure, and R, so I'm going to solve for moles. So we have 1.32 atmospheres times 2.5 liters equals 0.08206 liters atmospheres over moles Kelvin times 381 Kelvin gives us 0.1055, tracking at the third sig fig, moles of H2. It's almost like magic. Okay, so once I know moles of hydrogen, all I need is a mole ratio to get to moles of ammonia. That's the part of the stoichiometry that is the same. So moles of hydrogen gas, and it's a 1:3 ratio. So we'll end up with 0.035 moles of NH3. Okay, so the only thing that's new is the application of the ideal gas law to find moles. Okay, and I can't stress that enough. The stoichiometry is no different. It's exactly the same. So quick review. So the idea that kinetic molecular theory, the model where the gases are widely spaced, there's no interaction between the gas particles, and the average kinetic energy depends on temperature. Pressure is force per unit area, and it results from the collisions of the gas particles with surfaces. We have our gas laws that show how one of the properties of the gas varies with another. Combined gas law joins Boyle's and Charles. The ideal gas law allows us to calculate individual properties of the parts. And really, there should be a part here about Dalton's law and stoichiometry. I think there used to be a second slide part of this review. And there's not, but it's fine. So, but Dalton's law is individual partial pressures give us a total pressure. So the pressure of the individual gases add up to the total pressure of the system. And stoichiometry is nothing new. So the only difference with the stoichiometry here is that we're using the ideal gas law in order to get to our mole bridge.